everyone. My name is Daniel Choi. This is Team 11 YouTube presentation. My teammates are Bryce, Joshua, Jawher, and Kayla. My mentor is Glenn from General Dynamics Mission Systems. Our project was about investigating the efficiency of Rust programming language in real-time environments. This is our introduction. The C++ is one of the most common programming language used in embedded systems in DoD due to its high performance, but it has vulnerabilities associated with memory handling, such as buffer overflow, out-of-bound access, null pointer dereference. And these vulnerabilities have far-reaching consequences, such as data breaches, system crashes, and loss of system control. Rust programming language, on the other hand, incorporates memory handling mechanisms such as ownership, borrowing, lifetimes that ensure the memory safety of the embedded systems. So our project aimed to compare the performance between Rust and C++ on a Raspberry Pi connected to various sensors to validate whether Rust can meet performance requirements in real-time environments.
Hello, my name is Josh. I'll be going over research and use case. So during our literature review, we identified a gap between existing studies. The existing studies that we found addressed applications such as algorithms and computational workloads such as a cross-beam analysis. However, no literature was published covering real-time systems. So we addressed our project to work towards this type of system. To that goal, we had three main grading criteria when choosing our sensors. The first grading criteria is that it must be real-time data. The sensor must stream continuous data to be processed by the Rust or C driver. The second criteria was targeting UAS or UGV applications, specifically towards DoD unmanned systems, to ensure it's operationally relevant to our target stakeholder. Lastly, we targeted existing C code base. One of the goals of this project was to align with the DARPA Tractor Initiative to take existing software written in the C language and convert it to Rust and ensure that it is able to operate on existing hardware. Additionally, to maintain consistency across team member evaluations, we standardized our testing platform to hardware that was readily available, cost-effective, and fully supported by both Rust and C toolchains. For this goal, we selected the Raspberry Pi 4 Model B, utilizing 4 GB of LPDDR4 SD RAM and 32 GB microSD card storage. This ensured that all team members could run identical builds, reproduce results, and validate performance metrics across identical hardware configurations.
What are the trade-offs between C, C++, and Rust? On the left are some common issues with C and C++ programming language. You can accidentally read or write past the end of memory buffer, causing buffer overflow, the source of most crashes and security vulnerabilities in embedded systems. Also, memory has to be freed manually. It's easy to forget once or free it twice. When the file format changes unexpectedly, the code can also silently return wrong data. On the right is how Rust avoids these same issues. Every memory access is checked automatically at runtime, and debug builds and proven safe at compile time and release. Buffer overflow becomes impossible. Also, memory is always cleaned up exactly once, automatically. No leaks, no double free. Additionally, errors cannot be ignored. The compiler forces you to handle them, so you always know immediately when something goes wrong. During the design process, existing C and C++ code was modified by each team member to produce the desired metrics, being latency, CPU, and RAM utilization during iteration testing. Rust code was then developed to mirror the functionality of C and C++ code. This required local installation of compatible cargo builds to perform functions monitoring performance metrics identical to call functions executed in C and C++. To maintain the same functionality as C and C++, the cargo build was configured to interface with the same libraries included in the script. By implementing this tactic, the team ensured that call function differences had no impact on the result of the study, effectively isolating efficiency discrepancies to the programming language operating on the Pi 4 during testing. Here is the Wi-Fi sensor implementation, with libcap 1.10 enabling packet capture and libc enabling get R usage and system config, and more, integrated into both programs. The result is any observed efficiency discrepancy can be attributed solely to the language and its runtime, not to different APIs, parsing methods, or system call paths.
Our team developed a standardized data collection pipeline that utilized three main approaches. Firstly, a Python testing harness that consisted of a Python script that invoked the C and runtime drivers using identical runtime conditions to ensure the results were reproducible across multiple iterations. Secondly, automated metric collection that would log the metrics using system libraries into a running CSV data structure. And lastly, data visualization using the matplotlib library to ensure consistency in the displayed data. The metrics that were chosen to be captured was the average loop time, which is the wall-to-wall time to run each iteration, the average CPU usage, which would indicate relative processor usage, and average RAM usage, indicating total memory. Loop time was chosen because in real-time systems, they are dependent on predictable low-latency processing. Loop time directly measures how quickly each sensor can read and process the data. And faster, more stable loop times reduce jitter, improve responsiveness, and ensure the system meets real-time deadlines. Average CPU and RAM utilization was chosen to indicate whether the adjusted code could run on existing hardware, as the significant delta between the C runtime and Rust runtime environments would indicate a greater dependency on hardware configuration.
How do we delivered and communicated the final result of our performance study? After completing the data collection and code development stages, our goal was to present the findings in a clear and accessible way. To achieve this, our team developed a unified website interface that brings every major component of the project. Instead of switching between raw CSV files and individual chart and code windows, the interface consolidates everything into one platform. It includes separate sections for the C and Rust code, performance comparison graphs, real-time sensor outputs, summarized metric differences, and the hardware information associated with each sensor. As a result, the entire review process becomes smoother and much more intuitive. When interpreting the data, one of the most important findings was how closely Rust matched the performance of C in real-time environments. Across the sensors, timing remained almost identical, and in some cases, Rust even showed slightly lower latency. Additionally, CPU usage turned lower in Rust because more functions were handled locally rather than through callback libraries. However, the main difference appeared in RAM usage, where Rust required more memory due to its larger binary size and additional files needed to execute the program. Even with this overhead, overall performance remained highly stable. These results demonstrate that Rust can deliver real-time responsiveness comparable to C while offering significantly stronger memory safety guarantees. This is especially important for defense-oriented systems where security risk tied to memory safety issues can have serious consequences. Therefore, our results show that Rust can modernize C systems without losing performance, and it remains a strong, secure option for real-time applications.